Let's do it. Yo, what is up? It's your boy, Mark Jupiter T. Nah, let's do that again. Yo, it's Mark Jupiter T, and welcome back to another episode on the channel. This is the third episode, I think, of just really trying to, you know, get things done, I guess. And yeah, man. So here you have it. This is an overview of new product feature modifications. This is the introduction of the new inline engine M256. I don't know how new it is, probably 2015 or 2017 this engine was manufactured. So let's go to the first page. Engine 256, the six-cylinder spark ignition inline engine M256 with 48-volt electrification. The M256 as a spark ignition engine represents the start a new inline engine family from Mercedes-Benz and now replaces its successful predecessor, the V6 engine 276. The 48-volt electrification that was also part of the engine design process right from the start, along with a series of further innovative measures, means that despite the ambitious performance goals involved, it was also possible to achieve significant reductions in consumption levels. The beltless engine with integrated starter alternator exhibits an outstanding response characteristic across the entire RPM range. This is achieved through the use of an electric additional compressor, high performance exhaust, gas turbocharger, and the boost effect made possible by the integrated starter alternator, along with the implementation of 48-volt components. The range of technology in the innovative power plant includes further modules such as a variable control oil circuit, intelligent heat management, a gasoline particulate filter, and measures for reducing friction. The result is a carbon dioxide reduction of almost 20%, coupled with an output increase of more than 15% compared with the predecessor. The V6 engine 276, a six-cylinder engine, one that compares favorably with four-cylinder engine regions in terms of consumption, while the output can hold its own when up against the eight-cylinder engines. This is the second page. Brief description, new features, offset engine. An example, the cylinder bores opposite the crankshaft axis are offset towards the cold side, friction optimized engine, timing assembly on transmission side, crankcase well as the cylinder head made of aluminium. This is alloyed with zircon, which dissipates the heat even more efficiently. Cylinder barrels lined in nanoslide technology, iron carbon, engineered for a maximum combustion chamber pressure of 120 bar with sufficient reserves for further output increases during its service life. Engine carrier made of plastic, modular future compliant, exhaust system near engine mounted, integrated starter alternator, electric additional compressor, beltless engine, electric coolant pump, electric refrigerant compressor, and tried and tested 4 valves per cylinder, Camtronic on the inlet side, 2 camshaft adjusters for the inlet and exhaust sides, ensure optimized development of engine torque and improved exhaust characteristics, low noise chain drive system with silent chain, compact vane type oil pump with demand oriented flow control, third generation gasoline direct injection with 200 bar fuel pressure, piezo injectors and spray guided multiple injection, multiple spark ignition system for optimum ignition and combustion, multi-spark ignition. All right, third page, man. Location of M256. Number one, intake camshaft with Camtronic, piezo injectors, cooling duct piston, boltless engine, crankcase with nanoslide, barrel, near engine mounted Cadillac. Uh, I said Cadillac. Wow. I'm thinking of the car. At least we're on the topic of autos, but man, we're supposed to be reading near engine mounted catalytic converter, electric refrigerant compressor, electric coolant pump, and there you have it. As you can see over here, I cannot zoom in. I want to zoom in for you guys, but I can't do that. But here is the diagram or the picture of the engine. Looks beautiful. Basic engine, a design criterion for many essential technology modules in the long block engine, is CO2 efficiency. At the heart of uh, this was the reduction in friction, further optimization of the oil circuit through a split oiling concept, combustion optimizations, and the use of Camtronic with advanced intake valve closing. Friction optimization. Numerous detailed measures were implemented with the goal of further reducing friction losses caused by moving parts in the engine. This includes inline engine with 12 millimeter offset, discontinuation of belt drive through systematic electrification of all um, ancillaries, 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 ancillaries through the use of an integrated starter alternator, low friction shorter chain drive, crankshaft bearing with connecting rod oil supply for two crank pins, each consisting of a crescent supply groove in the basic bearing, piston with optimized piston rings, cylinder coating through latest generation of nanoslide technology, oil circuit optimization through pressure controlled dual circuit system and reduction in oil flow rate, use of low viscosity oil, crankcase and crank assembly. The crankcase is made from die-cast aluminum. The cylinder contact surface is machined with Mercedes-Benz patent twin wire arc spraying method. The nanoslide technology developed in-house significantly reduces friction losses compared with cast iron bushings. The twin wire arc spraying method sprays a layer of iron onto the pre-worked crankcase. The subsequent precision matching creates a dead smooth, friction optimized barrel that is highly wear resistant and so thin that an optimum transmission of heat to the coolant jacket is assured. The crankshaft and connecting rod are made of forged steel. The higher specific output increases the thermal and mechanical loads acting on the piston crown. To reduce these loads and to lower the temperature of the piston crown, the pistons are equipped with cooling ducts. The cooling helps to ensure stable combustion while also lowering the level of in-engine emissions. The piston cooling is integrated into the oil circuit's thermal management. All right, another picture diagram. There you go. Location, number one, cooling duct, piston, friction reduced, piston rings, piston pin. Oil circuit split oiling concept. An important development objective for the oil circuit was the high adjustment performance of the camshafts. This serves primarily to reduce emissions and realize a higher driving dynamics standard. The goal then is to supply the hydraulic camshaft positioner with the required level of oil pressure so that an adjustment at the required speed is already possible at idle speed. In a six-cylinder inline engine, the inhibitory average camshaft load moments generated in the main operating range place high demands in the oil pressure level. This is where the so-called split oiling concept is used for the first time. This refers to an oil circuit that permanently provides a stable, hydrocularly, hydraulically controlled high pressure for the camshaft positioner, along with a map controlled low pressure for the remaining lubrication points, using only one variable volumetric flow vane type oil pump to do so. The hardware for the low-pressure management system is integrated into the oil filter module to save space. A solenoid valve is used here to actuate a pilot-controlled piston, which opens up the necessary cross-sectional area between the high-pressure and low-pressure and the low pressure. A pressure and temperature sensor in the main oil gallery closes off the closed loop control circuit. The new system also presented a challenge in terms of the control software required. This was fundamentally adapted to the split oiling concept and expanded with the aid of further features to form a part of the intelligent thermal management. This also includes the delivery on demand piston cooling that was realized without the need for additional ducts and electrical actuators. The adapted consumer supply on the low pressure side ensures the lowest possible oil flow rate, while at the same time it is also part of the thermal management. During warm-up, particulate emissions can therefore be significantly reduced. The fast buildup of oil pressure when the engine is started, a high pressure level available from idle speed onward, and the advanced adjustment readiness of the camshaft positioner enable the required contribution in terms of responsiveness, issues, and consumption to be reached. Okay, here's two more diagrams for you guys. Pictures, there you go. Oil circuit, split oiling concept. We're still on that. Number one, oil module, heat exchanger, return spring, control plunger, oil filter cartridge, engine oil pump valve, high pressure, low pressure, uncontrolled oil pressure, engine top, front view, B4/4 purging pressure sensor, coolant temperature sensor, electric coolant pump, ME-SFI brackets, square brackets ME, close brackets, control unit, coolant thermostat heating element, and the purge control valve. There you go, guys. Feel free to always pause and just see like the pictures and the diagrams, so there you have it. Two more for you guys. View of engine from left. 19. Fuel system high pressure pump, knock sensor 1, knock sensor 2, crankshaft hall sensor, engine oil pressure and temperature sensor, quantity control valve, engine oil pump valve. View of engine from right, coolant thermostat, electric coolant. 25 was the coolant thermostat. Cylinder head and combustion, the high power to swept volume ratio of 106.7 kilowatts per liter with compact design, cylinder bore spacing 90 millimeters, bore 83 millimeters diameter, results in a high thermal load in the cylinder head. Charge air cooler is integrated to optimize the heat balance, which despite the high degree of supercharging involved, achieves excellent cooling of the compressed air. In addition to this, the charged air cooler also excels on account of its outstanding equal proportioning with a maximum difference of 5K across the individual cylinders. The installation of special exhaust valves also enabled the thermal load to be reduced. For the first time, sodium-cooled exhaust valves or valve halves been used as hollow flat seat valves that excel on account of the significantly improved level of heat dissipation compared with the previous hollow. Valves with a sodium filling in the stem, smaller exhaust valves, and a spark plug with higher thermal conductivity along with a smaller diameter thread M10 enable better cooling to be achieved in the head, thereby reducing the tendency to knock. Hollow flat seat valve. Number one, hollow stem valve, hollow flat seat valve. New with the M256 engine. There's a diagram of it. View of the engine from the rear, A79, integrated starter generator, pressure and temperature sensor, downstream of exhaust gas turbocharger, pressure and temperature sensor upstream of throttle valve, intake camshaft solenoid, and the exhaust camshaft solenoid. Valve train and camtronic. To achieve more economical timing, the adjustment range for the intake camshaft has been increased to a 70-degree crank angle (CKA). Apart from this, the M256 is also equipped with the Mercedes-Benz Chemtronic and example variable engine timing that makes two-stage stroke changeover on the inlet side possible. The combination of Chemtronic and variable camshaft positioner with large adjustment range enables a significant reduction in charge change losses and the lower load range to be achieved, both for a large valve lift through an Atkinson timing strategy, as well as for a small valve lift. Operation at a small valve lift requires combustion stabilizing measures to allow for the adverse flame development conditions caused by the significantly reduced charge movement and the lower mixture temperatures at the ignition timing. The fuel is introduced through several partial injections into the combustion chamber and flame development supported, if necessary, through multi-spark ignition. An asymmetric cam profile was also designed to further stabilize combustion through increased charge movement. The resulting swirl overlies the fuel/air mixture that is still in motion, and by doing so, it ensures more stable engine running at the lowest possible loads. View of the engine from above. B4/25 fuel pressure and temperature sensor, intake camshaft hall sensor, exhaust camshaft hall sensor, pressure sensor downstream of air filter, oxygen sensor downstream of catalytic converter, oxygen sensor upstream of catalytic converter, boost pressure control flap actuator, cylinder 1 and 2 intake Hamtronic actuator. Did I say actuator? Actuator. My apologies. Actuator cylinder 3 and 4 intake Hamtronic actuator, cylinder 5 and 6 intake Hamtronic actuator, divert air switchover valve. Function sequence for Chemtronic valve lift adjustment. With the Chemtronic valve lift adjustment, a map-controlled switchover between a low lift and high lift cam profile occurs for the intake valves in the intake camshaft. Basic input factors are the engine speed, load, and temperature. In the partial load range, the intake valves are actuated with the low lift cam profile. These do not therefore open as far and they close earlier. The short opening period in combination with a wide open throttle valve leads to de-throttling in the partial load range. While the lower valve lift reduces friction power, both contribute to greater fuel economy. The switchover depends on the driver's load request. Changeover is carried out by the following components: cylinder 1 and 2 intake Chemtronic actuator, cylinder 3 and 4 intake Chemtronic actuator, cylinder 5 and 6 Chemtronic actuator. The actuators are actuated by the ME-SFI square brackets ME close brackets control unit with a pulse width modulated signal. The intake camshaft consists of the following components: 6 machine cut cam pieces are mounted onto the carrier shaft. Each cam piece controls the intake valves of one cylinder. The Chemtronic actuators each actuate two cam pieces simultaneously. The cams themselves have the form of a double cam with two curved surfaces for each valve. If the steeper cam half is activated, the valve lift is increased and the valves remain open for longer. If the flatter half of the cam is switched to, the valve lift is shortened and the valves close sooner. If the engine speed increases or the load request is increased, the cam pieces on the intake camshaft are switched to the high lift cam profile. To do this, a coil in the corresponding actuator is energized, and a tappet moves in a corresponding curved track on the cam piece. With the rotation of the camshaft and the design of the curved track, the cam pieces are moved axially, and the high lift cam profile acts on the intake valves. An incline in the curved track then results in the tappet being returned to the starting position. To reset the camshaft to the low lift, a second tappet moves in the adjacent curved track and the reset correspondingly takes place. The position determination of the tappets is realized via an integrated Hall sensor in the actuator. Here's a diagram for you guys. Picture. There you go. View of intake camshaft from left. HF. So that's half. And then HS would be what? Well, I'm not sure. I was thinking HF would be the abbreviation of half, but I'm probably wrong. But there you go, HF. Flatter half of cam. Steeper half of cam. Curved tracks. Cam piece cylinder 1, cam piece cylinder 2, up to 6. Then you have the tappet, then cylinder 1 and 2 intake Chemtronic actuator, 3 and 4 intake Chemtronic actuator, and then cylinder 5 and 6 intake Chemtronic actuator. View of the engine from above. You have the T1/1 cylinder 1 ignition coil up to cylinder 6 fuel. Oh, wait. You have cylinder 1 ignition coil up to cylinder 6 ignition coil. Then you have cylinder 1 fuel injector up to cylinder 6 fuel injector. 6 cylinders. Exploded view of integrated starter alternator A79, integrated starter generator, and then N129 starter generator control unit. Integrated starter generator. The M256 sees Mercedes-Benz making a successful entry into a 48V on board electrical system. The energy storage unit used here is a 48-volt lithium-ion battery with an energy content of almost 1 kilowatts per hour, I'm guessing. The battery was able to be integrated very compactly and combined with a delivery on-demand cooling and heating system. In the P1 configuration, the integrated starter alternator is rigidly bolted to the crankshaft and is installed between the engine and the 9G Tronic automatic transmission. The power electronics are located in the installation space of the pinion starter, which is no longer installed. The task of the integrated starter alternator is to exchange energy between the drive shaft and the 48 volts on-board electrical system. It is operated here in two different ways. In engine mode, it can start a stationary combustion engine starter, as well as accelerate an already rotating drive shaft by supplying engine torque. So it does two things. So this one device, right, does or has, well, two jobs pretty much. That's the way I can explain it. Well, before the engine would need something to start the engine, and then it would need another device just to accelerate and give torque to the engine. Now this one thing just does both, which is pretty cool. And yeah, in generator mode, it can generate electrical energy, so it works as an alternator, and is responsible for supplying the 48 volt on-board electrical system as well as for charging the 48-volt on-board electrical system battery. The integrated design means that the torque is transferred without any integrated transmission elements between the integrated starter alternator and the crankshaft. The control unit for the starter alternator sets up the electrical connection between the three-phase AC system of the integrated starter alternator and the DC system of the 48-volt on-board electrical system. Built into the integrated starter alternator are a three-phase winding with permanent excitation, 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 a resolver for acquisition of the angular position, and two temperature sensors. Engine view from below. This is it. B40 slash 6 engine oil fill level sensor and the starter generator control unit. Have you read this before? No. Starter generator control unit. Okay, so there's the generator control unit. That's what we have seen in the page before. Charging. The objective behind the newly developed charging concept is to achieve the best response characteristic coupled with high engine outputs. The demanding installation space situation brought about by the exhaust gas emission control components located in the engine compartment, paired with the wish to achieve a high commonization level for the components in the engine family, were the decisive factors in opting for a single turbo concept. In order to achieve an impressive response characteristic in the lower speed range with the 320 kilowatts operated engine. Despite the naturally larger exhaust gas turbocharger, an electric additional compressor is used that, that is integrated into the 48-volt onboard electrical system. The exhaust gas turbocharger installed in the M256 is a twin-scroll exhaust gas turbocharger with air gap insulated exhaust manifold, including flooding separation for cylinders 1 to 3 and 4 to 6. The high level of vertical integration enables a particularly high quality low nickel steel to be used in combination with a special low-pressure casting for the turbine wheel housing. Special valve was placed on back pressure optimized gas routing. The design of the connecting points between the turbine wheel housing and manifold along with the leak tightness of the slip fits relative to each other. This design helps to significantly reduce charge change losses while also providing an excellent exhaust gas turbocharger response characteristic even where exhaust flows are at their lowest. Another advantage lies in the connection of low internal leakage rates and the manifold's air gap insulation. This helps to achieve a significant reduction in the surface temperature of the exhaust manifold, thereby relieving the thermal situation on the hot side of the engine, in particular on highly dynamic drives or during post-heating phases. To reach the temperature required for exhaust gas cleaning in the catalytic converter quickly, the electrically controlled wastegate and its forward stream were optimized for simulative best possible equal distribution. Okay, I'm gonna bring the brightness down, like just 4 points down, just because the sun is setting and it's getting a bit dark. All right. Design of charging system. Number 9. Charge air cooler, turbocharger, throttle valve actuator, electric additional compressor, divert air switchover valve, exhaust, charge air downstream of charge air cooler, charge air downstream of exhaust gas turbocharger, uncooled. And then let's read that one again. Charge air downstream of charge air cooler, which is cooled. Okay. Forced induction function sequence. The function sequence is divided into the following subfunctions. Function sequence for boost pressure control. Function sequence for bypass air. Function sequence for electric additional charging. Function sequence for boost pressure control. Boost pressure control is carried out via the boost pressure control flap actuator M16/7. The actuator is actuated in a characteristics map and loaded and load-dependent manner by the ME-SFI open square brackets ME close brackets control unit evaluates signals from the following sensors and functions of the engine management: charge, air, pressure and temperature sensor B4/32, boost pressure and charge air temperature. Pressure and temperature sensor upstream of throttle valve B28/26, boost pressure and charge air temperature. Pressure and temperature sensor downstream of turbocharger B28/17, boost pressure and charge air temperature. Pressure sensor downstream of air filter B28/11, intake pressure. Accelerator, pedal sensor B37, load request made by driver. Crankshaft hall sensor B70, engine RPM. Knock control, transmission overload protection, overheating protection. In wide open throttle operation, maximum boost pressure builds up. Where'd we go? Oh no. How far did we go? Okay. In order to reduce the boost pressure, the exhaust flow for driving the turbine wheel is diverted via a bypass by opening the boost pressure control flap. The boost pressure control flap actuator actuates via a linkage the boost pressure control flap that closes the bypass. Part of the exhaust flow is directed through the bypass past the turbine wheel, whereby the boost pressure is regulated and the turbine speed limited. In this way, the boost pressure can be adapted to the current load demand on the engine. To monitor the current pressure and temperature conditions in the charge air duct from the exhaust gas turbocharger to the charge air distributor, the ME-SFI open brackets, square brackets, ME close brackets control unit evaluates the signals from the pressure and temperature sensors and adjusts the boost pressure to the engine related requirements. Function sequence for bypass air. Should we read that or yeah, I guess we will do that. Function sequence for should we do that? For bypass air. The exhaust gas turbocharger continues turning for a period of time after the start of deceleration mode due to the inertia of the shaft, compressor, and turbine wheel. In the case of rapid closing of the throttle valve, charge pressure wave therefore runs back to the compressor impeller. This charge pressure wave would create a condition with a low delivery volume and high pressure conditions at the compressor impeller, which causes charger pumping, brief howling, and mechanical stress. Opening the bypass air switchover valve prevents this through rapid depressurization depressurization through a bypass in the intake side of the ATL. A schematic diagram of exhaust gas turbocharger. Number one, compressor, turbine to throttle valve from exhaust manifold, divert air switchover valve, fresh air, exhaust gases. When the engine is being operated under load, boost pressure is applied to the diaphragm, which then keeps the bypass closed. If the engine is switched off, the diaphragm is pressed into the seat by a spring integrated into the deceleration air switchover valve. If the ME-SFI ME control unit detects through the actual valve poten- potenti- potentiometers potentiometers M16 slash 6R1 and the M16 slash 6R2 that the throttle valve has closed and therefore deceleration mode is active. The bypass air switchover valve is activated, the diaphragm is pulled open against the spring force and boost pressure and opens the bypass to the intake side. The excess boost pressure is thereby relieved. If the engine changes from deceleration mode to operation, the bypass air switchover valve is no longer activated. The spring presses the diaphragm in the direction of the seat. The diaphragm is then pulled into the seat by the prevailing boost pressure, thereby closing the bypass again. Two diagrams for you guys, there you have it. Sectional view of the deceleration air switchover valve, 50 turbocharger, boost pressure control flap actuator, divert air switchover valve, status closed, and status opened. Yeah, you can see the airflow. Yeah, it's nice. View of the engine from left, B4 slash 32. Charge air pressure and temperature sensor. Pressure and temperature sensor upstream of throttle valve. Throttle valve actuator electric additional compressor. Function sequence for electric additional charging. The boost pressure is directly dependent on the RPM of the turbocharger that is driven by the exhaust flow. The boost pressure that can be generated by the turbocharger in the lower RPM range is therefore rather low and only increases as the engine RPM increases. When high power is demanded rapidly by the driver, it takes a certain time until maximum boost pressure can be built up so that the engine's full output is available. This behavior in supercharged engines is known as turbo lag. The counteract turbo lag and to have uniform high boost pressure available across the entire RPM range, the part of the boost pressure in the lower RPM range is generated by electric additional compressor M60/1. The available boost pressure can be up to a maximum of 450 mbars. Mbar. Okay. All right. The engine management calculates the target boost pressure at any engine speed according to the load request, the operating state of the engine, and the ambient conditions. As the exhaust gas turbocharger is unable to build up the target boost pressure in the low RPM range, the pressure difference between the actual boost pressure and the target boost pressure is compensated for by activating the electric additional compressor. To do this, the engine management system calculates the additional compressor RPM metered to the required boost pressure. Okay, so that was 450-meter bar, I'm guessing. Okay. Um, where were we? To the additional calculates the additional compressor RPM metered to the required boost pressure. The additional compressor is activated over an internal CAN bus by the SFI ME control unit in an RPM range up to 3000 RPM. The coolant-cooled electric additional compressor used with its output of more than 5 kilowatts provides a more spontaneous boost pressure buildup. It is positioned on the cool side of the engine, briefly before the inlet into the charged air cooler, where within a period of 300 milliseconds it reaches a speed of up to 70,000 RPM and a maximum pressure ratio of 1.45. During additional compressor actuation, the signals of the pressure and temperature sensor downstream of the throttle valve are registered to monitor the boost pressure when the turbocharger is running on its own. Pressure measurement is carried out via the pressure and temperature sensor downstream of the turbocharger. The electric additional compressor is located on the left engine side behind the charged air cooler between the exhaust gas turbocharger and the throttle valve. Any malfunctions occurring are sent to the MESFI control unit and are logged there as faults. A nominal speed can be manually specified with the aid of Zentree diagnostics. Exhaust treatment. As a member of the new engine family, the M256 also pursues the concept of a near engine mounted integration of the required catalytic converter volume to enable heating to be as fast as possible following a cold start. The M256 is also equipped with a state-of-the-art gasoline particulate filter (OPF). The catalytic coating used is a new development and is also optimized for back pressure. The lambda the lambda control takes place through a straight line lambda sensor upstream of the catalytic converter and a planar sensor located between the two catalytic converters. The complete catalytic converter box is fully insulated and has a modular design so that with the corresponding extensions, global emission standards can be met. The gasoline particulate filter (OPF) positioned in the first expansion stage in the upper body provides an effective means of significantly reducing the number of particulates. The operating principle of the gasoline particulate filter (OPF) technology is based on the diesel particulate filter concept, along with the sufficiently high degree of particulate separation. Yes, the lowest possible increase in exhaust gas back pressure by the gasoline particulate filter (OPF) is a decisive feature when using the vehicle. The gasoline particulate filter, OPF, volume itself was selected so that on the one hand an optimum filtration efficiently is achieved, while on the other hand providing sufficient volume for oil ash deposition in the OPF as mileage increases. Altogether, the modular design concept provides a high performance, back pressure optimized emission control system that is ideal for dealing with emissions under real life driving conditions, high output density emission for the new M256. Exhaust treatment 30 catalytic converter box, and then the gasoline particulate filter OPF. Okay, guys, I'm gonna switch on the light, man, but I'll be back like in a second, so I'm not even gonna cut this. Just gonna walk real quick. We're doing this like it's a live, bro. Like it's a live show, live recording. Okay, we're back. I've tried doing this thing of like recording live, but it doesn't work with the internet connection that I've got. Like it works for like till a certain point, and then it just lags out. And then all I got is like half of what I've recorded live. Anyways, location of exhaust system 30 catalytic converter box, gasoline particulate filter, center muffler, rear muffler, oxygen sensor downstream of catalytic converter, oxygen sensor upstream of catalytic converter, left exhaust flap actuator motor, right exhaust flap actuator motor. Exhaust system. The main exhaust system tasks are cleaning the combustion gases, discharge of combustion emissions from the vehicle, dampening of pressure surges that are generated by the explosive combustion in the combustion chambers, reduction of noise emissions. The design of the exhaust system um, acts exerts a distinct influence of the available torque in the engine's usable RPM range. The exhaust system participates passively in the charge change. The shape of the system influences the vibrations of the exhaust gas located in it. These vibrations support the discharge of the combustion gases from the combustion chamber when the exhaust valve is opened. The best result is achieved with the aid of variable timing and a flap-controlled exhaust system. The exhaust gas flap actuator motors operate the exhaust gas flaps in each exhaust tailpipe to minimize the noise level in the exhaust system. The exhaust gas flap actuator motors are actuated by the powertrain control unit by map-dependent control. Here, the exhaust gas flaps can be fully closed or opened, or they are continuously adjusted in a stored intermediate position according to the characteristics map used. The exhaust gas flap actuator motors can be diagnosed, and if the exhaust gas flaps are not opened, they send feedback to the powertrain control unit, which then reduces engine output. Depending on the set drive program various characteristics maps are stored for the opening. Characteristics of the gas flaps in the control unit. View of the engine from the right. 25. Coolant thermostat. M256/11. Electric coolant pump. Electric coolant pump. The electrical coolant pump is located at the front right on the engine, below the exhaust system. The electric coolant pump ensures needs-based circulation of the coolant in the engine's high-temperature circuit. The electric coolant pump is actuated by the MESFI ME control unit through a LIN signal. When this occurs, it is regulated after the following signals have been evaluated: coolant temperature, heater request, engine speed, engine torque. At a coolant temperature of less than 75 degrees Celsius, the electric coolant pump is deactivated unless the control unit for the climate control requests pumping capacity from the electric coolant pump. Here you go, another diagram. Picture engine cooling circuit. Number 1, radiator, expansion reservoir, temperature turbocharger. I don't know where I got temperature from. Wow. Turbocharger, combustion engine, oil module with engine oil cooler, heater return, heater feed, electric coolant pump, coolant thermostat, heating element, hot coolant return, cold coolant feed, ventilation slash coolant expansion, cold coolant heater return. Low temperature circuits 1 and 2, low temperature circuit component description. That was it, right? Here you go, another diagram for you guys. Picture. View of low temperature circuit. Number 9, charge air cooler, transmission oil cooler, low temperature circuit 2 cooler, low temperature circuit 1 cooler, coolant expansion reservoir for low temperature circuit 1 and 2, integrated starter generator, low temperature circuit temperature sensor, 48 volt on board electrical system battery, low temperature circuit circulation pump 1, low temperature circuit circulation pump 2, electric additional compressor, starter generator control unit, low temperature circuit switchover valve, low temperature circuit 2, low temperature circuit 1, expansion reservoir coolant line, electric refrigerant compressor. The electric refrigerant compressor is located at the left on the engine. The electric refrigerant compressor is responsible for intake and compression of the refrigerant. The electric refrigerant compressor is continuously speed controlled to match the evaporator temperature from 700 to 9,000 RPM. The electric refrigerant compressor is switched off depending on the outside temperature, the temperature of the high voltage battery, as well as after an accident. If the outside temperature temperature smaller than 2 degrees Celsius, the electric refrigerant compressor is generally switched off. The climate control unit actuates the electric refrigerant compressor via the control LIN 2. Okay. View of the engine from the left. A9/5 electric refrigerant compressor, electric coolant pump. Electric refrigerant compressor A9/5, number 1, spiral compressor, electric refrigerant compressor, electric motor, refrigerant compressor control unit, and power electronics. Structure. The electric refrigerant compressor control unit regulates the rotational speed of the electric motor and the quantity of refrigerant. The electric motor drives the spiral compressor. This consists of two inter intertwined spirals, of one one of which is permanently connected to the housing while the second rotates in the first one. The spirals here from the several increasingly smaller chambers within the coils. In these chambers, the refrigerant compressed in this manner reaches the center, where it then exits compressed. Guys, maintenance. I think that is it, man. Okay, second last page, guys. Here we go. Maintenance. The current Mercedes-Benz maintenance strategy also applies to M256. Country-specific um, deviations are possible. Europe fixed maintenance intervals with interval every 25,000 kilometers per 12 months, or is it slash 12 months? I don't know. And then China fixed maintenance intervals with interval every 10,000 kilometers, 12 months. USA fixed maintenance intervals with interval every 10,000 miles, 12 months. Service A and B always alternate. Additional operations are conducted during these intervals. Example Europe. Replace air filter element every 75,000 kilometers, 3 years. Replace spark plugs every 75,000 kilometers, 3 years. Replace fuel filter, spark ignition engines, 200,000 kilometers, 10 years. Draining of engine oil, the M256 no longer has an oil suction pipe and therefore no oil dipstick. The engine oil is drained using a drain screw in the oil pan. The oil level is checked using a sensor in the oil pan and through the display on the instrument cluster. This is called up using the steering wheel buttons. The procedure for the engine oil level measurement slash oil change is available in WIS document AP 18.00 dash P dash 1812 MKI using OM 654 in model 213. As an example, engine oils, the use of a gasoline particulate filter OPF year means that on this engine, the engine oil change is to be conducted with low ash engine oil. As for engines equipped with a diesel particulate filter DPF, for service purposes, the following engine oils are approved as per the Mercedes-Benz specifications for operating fluids. 229.51, 229.52, 229.61, 229.71. And then you have technical data shown here M256E30 DEHLAR. A, performance curve, and B is the torque curve. So here you have uh wow, how do I forget that? How do I forget that? Well, you have a scale over here, man. Okay. You've got, I'm guessing, meters by Newton meters, and then P. I don't know what P is. But then you have, oh, power. Power. Okay, so I'm guessing this is meters for the Newton meters, and then you have power for the kilowatts. So then you see over here, A is of course for the performance and B is for the torque. There you have it. And then shown here, M256 E30 DEH LEG performance curve and the torque curve. Variant of M256 for a market launch in Model 222. M256 displacement in I, output without ISA in kilowatts, and then torque without ISA in Newton meters. And yeah, you have the R and the G, and then motor, and then the cylinders, both 6 cylinders, both have the same cylinder bore spacing. Well, the specs are pretty much the same between the G and the R. Reduced output and increased output. What does that mean? I'm guessing it's still the same engine, it's just the output just varies. And then of course, yeah, you see that the output has increased, so the specific output in kilowatts slash I, and in the reduced output is 90, and then in the increased output it's 106.7. Same thing for the rated output. Okay. Well, guys, there you have it, man. There you have it, bro. This is the M256 engine by Mercedes Benz. And yeah, man. I don't know for how long we've been reading, but it was a good session. Good session. We'll be reading some more. And yeah. See you guys in the next.